Okay, guys, I'm going to get started. On Blackboard, you'll find a folder under the Labs tab for this week. It's got documents in it. They're numbered 1 through 4. And then there's a Excel document called blank. It's for us to do some calculations. It's a blank a table that I set up to make it easy for us to fill numbers in. So I'm going to open up document number 1, which is a Word document, I think, and it's a probability exercise. I'm going to go through these very quickly because I want to make sure that we get to the diagnostic test, because I think that's probably the most challenging thing for most of you guys in terms of what we're going to cover tonight, and it's the thing that's really going to haunt you in the future. That you're going to be dealing with it quite a bit. Okay. One of the things that we talked about is the idea of independence and exclusivity. Okay, so let's take a look at an example of something that's independent. Okay, so for instance, if I flip a coin might come up heads or tails. If I pick the coin up again and I flip it again, it could come up heads or tails. What occurred the second time is independent of what occurred the first time. The coin doesn't remember whether it came up heads or tails. Okay, so if I have a population of 1 million people and half of them are male and half of them are female, if I reach into that population and pull out one person, right, they come out male. If I go back and reach into that population again, well, the second sample is independent of the first sample. It's a big population, really that much of an impact. There's only 2 people there. Well, that's a little bit of a problem, right? Okay. How about mutually exclusive? What if I was looking at people that were left-handed and that had red hair in that population of 1 million people? While I can sample that, and each individual time I sample it, whether a person is left-handed or whether they have red hair is independent each time I sample. They're not mutually exclusive. In other words, you could have people that are left-handed. You could have people that have red hair, or you can have people that have both red hair and be left-handed, or neither. Right. So you have really 4 possibilities there. Right. So, but they're not mutually exclusive. You could have people that are both, or people that are neither, or people that have one or the other. Okay. So let's take a look at a couple of situations where we might, for some simple situations, we might be looking at probability where we're dealing with samples where things are independent and maybe mutually exclusive. Okay, let's say that we have a population where the prevalence of having insurance, in other words, percent of people in that population have insurance, is 80%. So if I reach out to that population and randomly select one individual in that population, what's the probability they're going to have insurance? It's going to be 80%, right? Okay, so now if I reach back out into that population, pull another person out randomly, going to be 80% again. Now, what's the probability that I would choose 3 people in a row? If I take one person randomly, second person randomly, third person randomly, what's the probability that all 3 people would have insurance? Well, first time it was 80%, second time was 80%, third time it's 80%. So we use something called the multiplication rule. 80% times 80% times 80%, or 0.8 times 0.8 times 0.8 is the probability that all 3 people are gonna be insured. Okay, so now let's look at a simpler version of that. The probability of flipping a coin and getting heads is 50%, right? Probability of flipping 2 coins and getting both of them to have heads is going to be 50% times 50%, which is 25%, 0.25, right? Well, how does that work? Well, the first coin could be a heads or a tails, right? Second coin could be a heads or a tails. So let's look at the possibilities. It's equally probable that you could have a head on the first coin, tail on the second coin. Tail on the first coin, head on the second coin, right? Or you could have heads on the first coin and heads on the second coin, tails on the first coin, tails on the second coin. 4 possible outcomes. Only one of the 4 outcomes satisfies that condition that they both have heads, right? So 25%. So you can look at it both ways. Just use the multiplication rule, or you could actually tease out all the different possibilities. If you like to play craps in Atlantic City, right? You want to know what's the probability of 11 coming up, right? Well, you got basically you got a coin, but you got 6 faces on that coin instead of, because it's dice, instead of 5 faces. So what's the probability of getting an 11? Well, there's only 2 ways of getting 11. You can have a 5 and a 6. It's 5 on the first and 6 on the second, or you can have a 6 on the first and a 5 on the second. Each individual roll, each individual outcome is equally probable, right? So there's 2 ways of getting an 11. How many different ways, how many different combinations can you have with 2 dice with 6 faces? Well, the first dice can be 1, 2, 3, 4, 5, or 6. The second dice can be 1, 2, 3, 4, 5, or 6. So if you got 1, you got 6 possibilities from that for the second dice. You got a 2 on the first, you got 6. You got a 3, so it's 6 times 6, there are 36 ways. 2 of those ways will give you 11. So what are the odds of getting an 11, rolling an 11 on one roll? It's 2 out of 36, which is 1 out of 18. Anybody ever play craps and you know what they pay off 11 when it comes up? Anybody ready? You look at the table there, it says how much they pay off. Anybody remember what it is? It's 15 to 1. Are you in good shape if they're paying 15 to 1? What are the odds of it occurring? 18 to 1. That house has a big advantage there. Don't ever bet 11 on the craps table. Right? There's much better bets on the craps table. It's very dramatic because it's 15 to 1 and stuff like that. But the odds of it coming up are 18 to 1 versus 15 to 1, which is the payoff. Right? So now you have an idea of like what you can look at in terms of all these different possibilities. Remember, I just mentioned to you, we have a population, 80% of the population is insured, right? And we decided, okay, multiplication rule. Since each sample we take is going to be independent, probability that we get 4 people, if I randomly pick 4 people, probability they'd all be insured would be 0.8 times 0.8 times 0.8 times 0.8. Okay, that sounds good. What's the probability I would pick out 4 people from that same population that are all not insured? Anybody want to hazard a guess?
0.2.
Ah, great. You guys, you're geniuses. You really, you get, if you start to think about this simply, you can really get this stuff, just not get frightened by it. Okay, so now what's the probability that 3 out of 4 people would be insured? That gets complicated now, doesn't it? Right? Because now, instead of having only one possible outcome, where I told you what's the probability all 4 would be insured, so you know the probability the first person 0.8 times 0.8 times 0.8, 0.8. Now I've made it complicated because 3 out of 4 people insured. It could be the first person is insured, the second person isn't insured, third and fourth are insured. But there's other ways that this could happen. First person's insured, second person's the third person, maybe the guy that's not insured. So there's many possible ways you can get that outcome. Okay, so now things get a little bit more complicated when we're not dealing with all or none kind of situation. We're dealing with the multiplication rule. Okay, so now let's take a look at an example of where that might be occurring. Okay, so let's see. Let me ask you this. Let's see. I'm going to say 80% of the population is insured. So the probability I would pick 3 people out and all 3 of them would be insured is going to be 0.8 times 0.8 times 0.8. Somebody do that quickly for me on a calculator. Right? It's 0.64 times 0.8. What's that? 0.512. About 51% is the probability that all 3 of them, 0.8 times 0.8 times 0.8, but you have about 51%. In other words, 49% of the time, I pick 3 people randomly from that population, and I wouldn't have an outcome where all 3 were insured. So 51% of the time. Let's say that you took 3 people from this population, did this 1,000 times. So you had a really big sample. And you found that 75% of the time, all 3 of them were insured. Now, the prevalence of the population is correct. It's 80%. What would that tell you, since you found that it was really that the probability of getting all 3 insured? What would that tell you about your sampling? Right? Would that tell you a couple of things about that there's a problem there. We should have gotten 51%. So what could that tell you about your sampling? Maybe your sampling is not random, right? There could be some bias in the way that you're sampling. Or maybe the probability of being insured is not independent. So for instance, let's say it may not be independent, because if you're picking people as they walk into this room, they may walk into this room in family groups. And family groups are a lot more likely to be insured than individuals in the general population. So it may not be in the people in this result you're looking for may not really be independent or mutually exclusive, and your sampling may not be truly random. So if you see an outcome like that, where it doesn't match what you predicted, you have to figure there's something wrong with the sampling, or perhaps the variable you're looking at is not truly independent in the population. Okay, so that might be a little bit of a trick question on an exam or something like that. Yes?
Could it also be that the number of repetitions?
Yeah, it should. That's why I said 1,000. 1,000 is a ridiculous number. When we get into sampling and stuff like that, when we talk about a large sample, we're talking about 30, 40, 50 people is a large sample, or 30, 40, 50 cases is a large sample in a study, say in a drug study or something like that. 100 people is a gigantic sample. Right now, there are studies that that used thousands and tens of thousands of people. You know, the Framingham study, where they studied the rates of heart disease, where they were looking at very low prevalence events that occurred over long periods of time. So they needed really big samples to tease out, the relative information they needed. But very often we're dealing with sample sizes that are much smaller than that when we're trying to evaluate things. Big samples means a lot of work and a lot of time and a lot of money invested, right? So that's one of the reasons we're learning statistics, because if we wanted to know absolutely whether eating Twinkies caused high cholesterol, we would ask everybody in the population how many Twinkies they ate and how many people had high cholesterol, right? We not get a sample of everybody, right? But that's not practical. So we have to get a smaller sample size to make these studies practical. Now, once we get a smaller sample size, probability is involved now. We could be fooled by our result. In other words, if I only sample 30 people that eat Twinkies and 30 people that don't eat Twinkies, well, now I have a relatively small sample size relative to the general population. So now I just might get, I might get 30 particularly healthy Twinkie eaters, right? And have the bad luck to get 30 particularly unhealthy non-Twinkie eaters or something like that. But what we're going to be learning in this course is how to figure out how the sample size, how the variability in the population, how that impacts how likely we are to be correct or incorrect when we make our prediction based on a study. That's what really this is all about. You want to be able to describe a population, to evaluate a relationship or a correlation. You want to be able to evaluate that by taking a sample rather than to examine the entire population. Is there any situation where we actually survey the entire population? The census. Every 10 years, we get certain kinds of information about the entire population, right? And that's valuable information. But sometimes there's problems with the census. What's one of the problems that we have with the census? I'm sorry? They don't get everybody, do they? Right? They undercount certain populations, right? Immigrants, illegal immigrants, even legal immigrants, they tend to undercount. We know that happens. It happens right here in New York City. And we could correct for that. In other words, one of the things, how do we know that happens? Well, they go back, they send census takers out into the community, and they do aggressive searches for people that they missed. So they know that if they went into the zip code and they found they were undercounting Hispanics by 7%, they could say to themselves, hey, maybe we need to adjust the census to account for that undercount. They don't do that. Anybody know why they don't do that? Is it a political thing? It could be, right? It could be a political thing. Actually, it's more than that. It's in the Constitution. It's got to be a physical count. You can't adjust. Even if you know it's incorrect, you can't adjust it. And you won't be able to adjust it unless you have a constitutional amendment to adjust it, right? So the Constitution says you have to do a physical count. You can't rely on statistics to do a census. Okay, interesting, right? All right, so let's move on from this. Okay, I'm going to move on to the second document, okay, which I discussed probability trees. Okay, now, remember we talked about the fact that, okay, well, these probabilities are the same. Okay, well, in fact, we can apply this as long as they're independent events. We can apply different, in other words, it doesn't have to be a single outcome for all three people or all four people or cases and so on and so forth. We can apply the same multiplication rule to a number of different situations. So I'm going to do it with coin flips. And the way I'm going to do it with I'm going to start with coin flips. I'm going to need a blank piece of paper to write on here. Let me find it. And on this document, I go through a couple of examples of it here, but I'm going to start here with a fresh document. Let me just make sure I'm okay with people online. Okay. And not so much confounding variables on as much as the idea of whether something's independent and exclusive. We're going to be talking about confounding variables as we move forward. Okay, so now I'm going to start with coins. And I'm going to say to myself, I'm going to take 3 coins and I'm going to flip them. And I'm going to see what the outcomes might be. Okay, so first thing I'm going to do is, let's see, first coin I flipped could be a head or a tail, right? Probability of getting a head is 50%, right? Probability of getting a tail is 50%. Now, if that first coin came out heads, the second coin that I flipped could be either a head or a tail. The probability of getting a head is 0.5. Probability of getting a tail is 0.5. Same thing if the first coin were a tail. Probability of getting a head is 0.5. Probability of getting a tail is 0.5. Okay, so next I'm going to take a look at what the third coin would be. Well, if the second result of the first, if second result was a heads, well, now another 0.5 times and another 0.5 for heads or tails on the third coin, on that coin, and then again also for this outcome, tails, heads, and then what is the outcome? The last coin could be heads or tails because the coin doesn't know what the previous outcomes were. Tails, and over here for the tails, heads, tails, 0.5. I just drew a probability tree. In other words, every probability, every outcome is represented here. Probability of getting heads, heads, and heads is equal to, what's it equal to? 0.5 times 0.5 times 0.5. Right, which is 1/2 times 1/2 is equal to 1/8 or 0.125. What's the probability that I would get heads, tails, heads, heads, tails? Right, same thing, it's going to be 0.125. Right, so this is heads, heads, heads. This is heads, heads, tails. Right, okay, now about heads, tails, heads, tails, heads. 0.125. Heads, tails, heads. Okay, same thing for heads, tails, tails. Right, all these are same because it's 50%. They're all the same likelihood. How about tails, heads, heads? Tails, heads, heads. Tails, heads, tails. And then tails, tails, heads. And then finally, tails, tails, tails. Okay, so what's the probability of getting all 3 heads? There's only one way that it can occur. That's 1/8, right? 0.5 times 4. And that works out just the way we expected. How about the probability of getting all tails? Same thing, right? Doesn't really matter. How about the probability of getting 2 heads? Well, here's one way to get 2 heads. Here's another way to get 2 heads. Here's another way to get 2 heads. That's 3 out of 8. That's 0.375. And the probability of getting 2 tails and a head is going to be the same deal, 0.375. What do you think these are all going to add up to when we add them up? Yeah, they're all going to add up to 1, all the different possibilities. Now, our insurance situation that we're just looking at, Well, the probability, instead of looking at it from the perspective of probability getting heads or tails, what's the probability of being insured versus not insured? Well, now the probability is 0.8 versus 0.2. And you just work your way through the whole thing again, and you could actually use this to calculate. I'm not going to do it because it's going to kill too much time. But you could actually do this now if you substitute insured for H and uninsured for T, and for heads you use 0.8, and for tails you use the probability of 0.2. You could actually go out with all the possibilities, multiply them out, and find the probability of all these outcomes. And you'd be able to add up all the times that you got 2 people insured and 1 not insured. And then you could calculate the probability using this probability tree for the probability of 2 people being uninsured, or 1 person being uninsured out of the 3 that you select. Okay, so this, as long as they're independent, you can do this kind of you can apply this multiplication rule. Okay, so kind of cute, right? You can play around with that a little bit. Let's move on to something else now. And that is, remember the table you just looked at? That crosstabs table or that contingency table? I'm going to blow this up a bit. Okay, this is a similar kind of table. And this is the marital status of the U.S. population that's 18 years plus in millions. When this was done, this data is from a number of years ago. There were 214 million adults in the U.S. population at the time this table was put together. And of those, 104 million were males, 109 million were females. Okay, so right off the bat, let's see. If one person is randomly selected from the population described here, what's the probability that person is divorced? Well, what's our total population? 214. How many people in this population are divorced? Right. So what's the probability that your random selection would be a divorced person? Simple enough, right? Okay, that's fine. What's the probability that the person is male? 104 over 215, right? Right? That's the probability of A over the probability of A plus B, the total, right? They're male or female. A little bit more complicated if you wind up looking at all the other different possibilities. What's the probability that the person is a male and a widower? Now, what is that an example of? That's what is that? Is that a union or an intersection? That's an intersection. You're only looking at the people that both of those properties apply to. Okay, so what's the probability that they are a male and a widower? 2.7 over 214 million, right? Okay. Given that the person is male, what is the probability that he's married? What is that? That's a special kind of probability. It's a conditional probability. Given that one condition has already occurred, now what's the probability of this other condition occurring? Okay, if I had just asked you, what's the probability that a person is married, right? That would be 126 million out of 214 million. But now I've said, what's given a person is male? So now you're only looking at the males, right? And what's the probability that that person would be married if he's male? Is 63 million over 104 million. Okay, that's a conditional probability. When we get into looking at a diagnostic test, that's going to be an important distinction for us when we look at predictive values for tests. What's a predictive value for a test? Well, that means, for instance, if you get a positive result on your test, what's the probability you really have the disease, right? Predictive value. Okay, so in other words, given that you tested positive, what's the probability you have the disease? You have a condition that you have that's already been satisfied. With that condition satisfied, what's the probability? It's different than the prevalence in the population, which is just the probability of having the disease, right? So we're going to take a look at that when we get to that. Okay, so now let's open up number 4. Oh my goodness, we're already at 8 o'clock. Man, this is brutal. If you have to go, bail out. If you can stay for about 10 minutes, let me go. What's that? Oh, I'm sorry. Oh, wow. In most semesters we teach this 5 to 8, right? So, oh, good. I feel so much better now. All right, good. I can go. I was saying to myself, how can I explain this in 10 minutes? Oh, God. Okay, good. All right. Let me just check online, make sure nobody fainted when I said that. Okay, good. You guys are still there, I hope. Good. Okay. All right. I'm gonna take a look at this other. I'm gonna open up this. Document called number 4 diagnostic test nickel, and I'm gonna open up this blank Excel file, this table for this blank Excel file. Right. So this is actually a contingency table or crosstab. In the columns, I have whether a person has disease or they don't have the disease. In the rows, whether the person tests positive on a diagnostic test or that they test negative on a diagnostic test. Okay, so I'm going to read this description of this diagnostic test. And this diagnostic test is for sensitivity or the test if you're allergic to nickel, if you have a sensitivity to nickel. I'm going to use the word allergic to nickel from now on because sensitivity is a special word for us now. Okay, so I want to know if you're allergic to nickel, right? Well, we took the 100 subjects that are known to be sensitive to nickel, right? Were tested with this new screening test. Well, the screening test, why do we want a screening test? We want a quick and easy way to test whether people have a nickel allergy. Nickel allergies are on the increase lately. Anybody know why? Right? Nickel is in a lot of metals. It's an alloying element in a lot of metals. Stainless steel, it's in gold, brass, a lot of stuff. And what's gotten pop? When I was younger, tattoos were like you were like a rebel if you had a tattoo. Nowadays, you run into people who have these piercings like everywhere, right? A lot of those piercings are made out of metals that, among other things, contain nickel. People have stainless steel backs on their wristwatches, right? So there's a lot of contact that they run into with metals that contain a nickel, and as they perspire, it dissolves a tiny bit of that metal, and they get a rash or they have some sort of reaction to it. Usually a rash, skin rash. So it's getting more and more common, sensitivity to nickel. So now, what do you usually do when you go to an allergist? What do they do to test you for sensitivities? They do a patch test, right? It's like a challenge test. Well, they got to poke you with stuff and they got to make you go away and you come back and they look to see if your arm blew up and stuff like that. It's kind of a nasty test. So let's say we had a simpler, quicker office test. Somebody invented a test like this. That's what happened here. Somebody invented a test. This pharmaceutical company invented this screening test, something that doesn't have to be as accurate as the gold standard test, but is cheaper, easier to do, and is a good screening tool for nickel sensitive allergies. So let's say he wanted to test this. So he would go out and he would look for people that have known allergies to nickel. So he would gather 100 subjects that are known to be sensitive to nickel, and he would use this test. And in this case, 80 of those 100 people tested positive. All of those people have a nickel allergy. They're all positive for nickel allergies. 80 out of the 100 tested positive. So 80% of the time, it correctly identified people that are allergic to nickel. That's called the sensitivity of the test. If it had gotten 100 out of 100, the sensitivity of the test would be 100%. If it had gotten only half of it, the sensitivity of the test would be 50%. That makes sense to everybody? Okay. So now that's called the sensitivity. Now he also said, well, let me test it on people that I know are not allergic to nickel, right? And see if it really tests negative. And in this case, those 100 subjects, he found that 90 of them it correctly identified as not being sensitive to nickel. But that means it got it wrong 10 times. It said 10 out of those 100 people who are not sensitive, it says that they were sensitive. But it got it right 90 out of 100 times. So it was correct at predicting that they weren't sensitive, they weren't allergic to nickel 90 out of 100 times. That's called its specificity, right? The sensitivity of this test is 80%. Means 80% of the time it correctly identifies people that are allergic to nickel. Its specificity is 90%. 90% of the time, if you get a negative result, you don't have an allergic, you're not allergic to nickel. Okay, but there are, like times it gets it wrong both ways. Okay, so let's take a look at this. We're going to actually apply this now. Okay, let's say that you have a population where the prevalence of nickel allergies is 20%. Okay, let's see how this is going to shake out. Okay, I'm going to take that table that we have here, and I do this in kind of an unusual way, right? So it might be a little bit different than what your textbook looks like, but I think this makes it a little bit simpler to understand what's going on here. First thing I'm going to do is I'm going to say to myself, well, what exactly is going on here? Let me just make sure this is centered. Okay, if a person has a nickel allergy and they test positive, what's that going to be called? That's a true positive, right? It can be positive or negative, and it can be correct, true, and it can be incorrect, false. Okay, what about a person that has a nickel allergy but tests negative? Okay, that's a false. Okay, that's a false negative. They tested negative. How about a person that doesn't have a nickel allergy? How about a person that tests negative and doesn't have a nickel allergy? What are they? They're a true negative. Okay, true negative. What about a person that tests positive but doesn't have a nickel allergy? That's a false positive, right? Okay, so look what happened here. The positives are all across the top row, because to be positive, you have to be in the top row, right? Okay, right? And to be negative, you have to be in the bottom row, right? Those are all the negative tests. Now, it gets a little trickier looking down the columns. Now, in the person that tests positive that has the disease is a true positive. But if they test negative, they're a false negative, right? So it gets a little confusing with that. Person who doesn't have the disease or condition, right? When you get it right, they're a true negative. But when you get it wrong, they tested positive. If they don't have the disease, that's the wrong result. So that's a false positive. So it can get a little tricky. And if you really want to, you can actually keep these, keep a table aside that includes these descriptions, and you can actually use formulas or something like that to help you fill it in rather than do it intuitively. Now, what did I say the prevalence was again? Okay, prevalence was 20%, 0.20. Okay, so now I'm going to take a population of, I'm going to call it 1,000 people. Okay, in a population of 1,000 people, if the prevalence is 20%, how many of those people would I expect to have that condition? 20% of them, right? 200 people. I would expect 200 people out of 1,000 to have that condition. How many wouldn't have the condition? 800, right? Pretty straightforward. Let's say I apply this diagnostic test to this population. Okay, so if I apply this diagnostic test and I said the sensitivity was 80%, and I said the specificity was 90%, right? If I said the sensitivity is 80%, I'm saying that if you have the condition, it'll correctly predict that you have the condition, test positive 80% of the time. So how many people have the condition? 200, right? How many people are going to test positive? It's going to be 200 times 0.8. Right? It's going to get it right 80% of the time. That leaves how many people that don't have it? Right? That don't test positive? 40. It gets it wrong 40% of the time. Those are our false negatives. Right? Okay, let's do the same thing with the people that don't have the disease. The specificity is 90%. That means it's going to get it right 90% of the time. Which of these boxes are where it gets it right? Disease negative, test negative. That box is where it gets it right. It's going to get it right 90% of the time. So for 800 people, it's going to be right 90% of the time. Okay, which is 720 people. Okay, how many does that leave where it gets it wrong? 80. The other 10% of the population that don't have the disease. Okay, so Out of these 1,000 people, how many tested positive? The total number of people that tested positive is going to be equal to 160 plus 80. The true positives and the false positives. How many people tested negative? It's going to be equal to the sum of the it's going to be sum of the false negatives and the true negatives, the row across. So if I asked you, if you test positive, if you go to your doctor, he applies this test, what's the probability that you have a nickel sensitivity given this test? You go to the doctor, you test positive. Now it's a whole new ballgame. This is a conditional probability. Given that you've tested positive, what's the probability you actually have the disease? Well, let's look at our population here. How many people, this is going to be our positive predictive value, how many people in this population tested positive? 240. How many people actually, of that group of 240 people, how many actually have the condition? Right, so your positive predictive value is 160 over 240, okay, which is about 2/3, 67%. So that means that 1/3 of the time you won't have that condition, right? So you'll test positive, you'll have to go for treatments that you don't need, you'll have to go for a more invasive test, a more expensive test, and so on and so forth. That's why positive predictive value is an important thing for a test. Now, let's take a look at another element of this. If you test negative, what's the probability you're really negative? Negative predictive value. How many people in this population tested negative? 760. How many of them really are negative? There you go. 720 over 760. Okay, 95% of the time, if you test negative, you really aren't. You really do not have the disease. Now, does this ever come up anywhere? Let's take a quick look online. Let's see. I'm going to pick out Pap smear. Positive, predictive. I spelled it wrong. Value. See what comes up. Pap smear had a sensitivity of 83%, specificity of 98%, so on and so forth, blah, blah, blah. These tests, you will actually find information published about this, right? If you go and look online, or if you go through the various databases that we have here at Hunter that you have access to, you can actually see research on different kinds of diagnostic tests. And one of the things you'll see is sensitivity. You'll see specificity. You'll see what the positive predictive value of these tests, because these are important measurements for understanding how reliable a test is, right? Now, as it happens, we're going to look at something, let's see, 83%. That sounds pretty good, doesn't it? And a specificity, 98%. That sounds great. 83%, 98%. Sounds really good, right? Sounds really a pretty good test. We've got a problem with this stuff, and we're going to see what the problem is in just a moment. Okay, we're going to go back to our example that we just did right now on the sensitivity, and I'm going to change an element of this. And the element of this that I'm going to change is going to be the prevalence. Okay, now this time around, I'm going to copy this out of here. Put that up there, put that aside for a little bit. Okay, now this time around, I'm going to say the prevalence now for, let's say it's the same test, exactly the same test, except this time the prevalence of this condition in the population is 1%. That's the prevalence in population now. Sensitivity of the test is still, what did I say it was, 80%. The specificity of the test is still 90%. Let's figure this out now. Okay, you got 1,000 people. Okay, it could be a population of 1 million. I'm going to call it 1,000, keep our numbers simple, right? If the prevalence is 1%, out of 1,000 people, how many would you expect to have that condition? 10, right? 1% of 1,000 is 10, right? Okay, now the sensitivity is 80%, right? So what's the probability that you would get it correct for those 10 people? 80%. So how many of those 10 people would you expect to get true positives on? 8. That would leave 2 that you would be wrong on. Okay, now that would leave 990 people who don't have the disease, don't have nickel sensitivity. Okay, so now what's the probability that you would get that right? It's going to be 990 people times 0.9, right? You'd get it right for 891 of those. How many times would you get it wrong? What's the difference between those two? What's left? Right? It's equal to 990 minus 891. It's going to get it wrong 99%, 99 times for those people. Right? Same sensitivity. It's the same test. Nothing's changed on the test. Only that's changed is the prevalence of the disease in the population. Okay, so how many people were positive? 107. How many people were negative? 893. Okay, now let's calculate our positive predictive value. How many people tested positive? Let's see, how many people tested positive? 107 people tested positive. Of those 107, how many actually had the disease? 8. 8 over 107. If you get a positive test, what's the probability you have that disease? 7%. Right? 93% of the people who test positive with this test don't have the disease. What did we just see the sensitivity was for pap smears? 83% or something like that, right? Is the incidence of cancer for people taking pap smears, is that very high, that prevalence? How many people in the population, how many women in the population at any given time? What percentage of the population, what would the prevalence be for uterine cancer, let's say, at any given time? Maybe it's 0.00015 or something like that. It's a very low prevalence disease, right? So if you got a test that has 83% sensitivity, what's that going to mean for pap smears? That means that most women, enormous number of women that get a positive pap smear don't have cancer. But it leads to much more invasive testing. Anybody know of any other similar tests that are for low frequency, low prevalence diseases in the general population or in the population you test that have a problem with a lot of false positives? PSAs, right? For men, right? Relatively low incidence of prostate cancer, but a test that doesn't have a great, has an okay sensitivity, but not great. So you get a lot of false positive prostate cancer. So many now that a lot of doctors ignore they use their own judgment about whether or not how to react to elevated PSA tests. How about breast cancer, mammograms? Again, a lot of false positives in the mammograms, so that means there's a lot more testing goes on, more expensive and more invasive procedures, right? So that's a problem. So you see how good a tool this is for understanding a test. Positive predictive, let's look at negative predictive value here while we're at it. That's going to be pretty good, isn't it? Right? So if you test negative, right, that means that, let's see, 891 people out of 990 that don't have nickel sensitivity, the sensitivity, it's actually, I have to make it show us another decimal place now. Oops, is it only 90%? Oh, I'm sorry. Yeah, excuse me. I went into the wrong cell there. Let me do that again. Let me do the whole thing again. That's equal to there's 891 people who tested negative out of 893 that were actually should have been negative. And in fact, it's more than 99%. Right? Rounded up to 1. It's not actually 1. Let me just make sure that you can see that it's not actually 1. Okay, let's see. There you go. That's the percentage. Really good predictor of that. However, now you got the other problem where we are on the other side. The sensitivity is an issue for us because not so much because sensitivity is terrible for the test, because it was the same as it was before, but now because it's such a low prevalence condition in general population. So now, if we had a problem like this, and maybe I'll give you a couple of examples you can play with on your own, you'll be able to get an idea of what the positive predictive value means and how to calculate it. Okay, so now, in that same vein, I just want to show you something. I don't want to force you to do this calculation because it can get a little obnoxious, and I really want to make sure that it's something that you really need to know. In your readings, in the lecture, I don't remember it coming up. I might have been out of the room at the time. Did Bayes' theorem come up? Okay, good. Okay, good. I'm gonna bring it up here now so that you at least know about it. Okay, there is a relationship that describes conditional probability. This is called Bayes' theorem. This is a way of calculating a conditional probability. Okay, so let's read this. What does this mean? What does this say? Okay, that pipe symbol, that up and down straight bar over there, is called a pipe, and it means given that. Okay, the probability, given that A has occurred, the probability that B occurs. Probability of B given that A has occurred. Okay, and that's equal to the probability of A given that B has occurred times the probability of A over the probability of B. Sounds like, where did somebody put, why would I even ever want to know that? And how did they get to that point, right? It's a little confusing. Derivation of this can be a little bit challenging. So I'm gonna skip over that and just give you an example of where that might be of some interest. Now, what does that actually mean? Let me read that again. Okay, the probability of A given that B has occurred is equal to the probability of B given that A has occurred. So let's say that A represents the probability you have disease, and B represents the probability that you test positive, right? A is the probability of having the disease. B is the probability that you test positive, okay? Okay, so the probability that you have the disease given you that you test positive, that's the positive predictive value there, right? P of A given B is the positive predictive value if you define A as the. We're going to get to that. We're going to get to that. I'm working my way towards that. So now, what is that? What is that positive predictive value? Well, it represents the probability that you have all the people that have. Remember, we went across the row, and the number of people actually tested positive. Here's the number of people that tested positive down here. Probability you test positive. Remember, B was probability testing positive. So that was the number that we looked at here. Whoops. Did I close that? I lost it. Let me see. Maybe it's still here. There it is. Remember when we did positive predictive value? It was 107. That's all the people, the probability of testing positive. It's all the people that tested positive, right? So the bottom half of this is the people that tested positive, right? And the top half is the probability that you tested positive, that you tested positive given that you have the disease, right? What is that? That's the sensitivity, isn't it? Probability you test positive given that you have the disease is the sensitivity. And the probability that you the probability that you have the disease, that's the prevalence, right? So if I look at this, this is the sensitivity times the prevalence. This is the number of people that tested positive, right? That actually tested positive correctly and have the disease. And this is the total number. That's the total number of people that tested positive. So this is kind of describes what with the situation that we have. The only problem is the probability that you test positive gets a little complicated, right? Because the probability that you tested positive, there's two ways to test positive. One is to test positive because you have the disease. The other way is to test positive because the test was wrong and you're one of the false positives, right? So I can expand that same formula into something that looks nasty like that, right? Okay, and what is this? The top part is what we just discussed, the sensitivity times the prevalence, right? So you get the people that actually tested positive and have the disease, right? Test positive given they have the disease times the prevalence. And down here is the people that tested positive correctly, right? Because they had the disease, just like up here. And the people that were false positives that tested positive because they're false positives, right? And the way that's calculated is the probability that, I've lost track of this. The probability that, you see how confusing this is. But don't worry, don't get too fixated on this, but you get the idea here. There's two possibilities here. Test positive given you have the disease, and you test positive when you incorrectly when you don't have the disease, and you do that by doing the inverse of the other one. In other words, this is 1 minus A prime is 1 minus the prevalence. This is the probability of not having the disease. Like for the nickel, it would have been, if the prevalence were 80%, this would be 20%, and the probability of testing positive if you're in that 80%. So there's two ways. This would represent probability of false positives, probability of true positives. So this is all the positive tests, and these are the people that actually have the disease up here. If I take this whole thing and actually turn it into a formula, it looks something like this. Maybe this is a better view of it. Let me blow that up. Okay, probability you have the disease, given that you test positive, is equal to the probability that you test positive, given you have the disease, right? Sensitivity, times the probability that you have the disease over the two ways that you can test positive. Probability that you test positive, given you have the disease, times the probability, the prevalence, probability of having the disease, plus the probability of testing positive, given that you don't have the disease. That's our false positives, given that you don't have the disease. In other words, the 1 minus the prevalence, right? So if I go down here to this very last version of this, okay, I can actually, if I tell you, if I don't give you that silly table with my examples, my fake little population and stuff like that, if I just told you the sensitivity, the prevalence of the disease in the population, and the specificity, you have everything you need to calculate the positive predictive value. What do you need to do? Do you need to go through the steps I just went through? No. All you need to do is go to this last part where you actually find those three elements that are here, and you say, well, the probability of A given B, the probability of having the disease A, given that you tested positive, is equal to the sensitivity times the prevalence over the sensitivity times the prevalence plus 1 minus the specificity times 1 minus the prevalence. If we do that now, we'll wind up with the same prevalence that we did before. Okay, let's give it a try. I'm going to give it a try on the first version of this that I did. Okay, see if this really works for us. Okay, so what's the top part of this equation? It's the sensitivity times the prevalence. Okay, so what is that? The sensitivity times the prevalence is equal to sensitivity was 0.8 times the prevalence, which was 0.2, right? 20% of the population. Okay, let's look at the bottom of this equation. The sensitivity times the prevalence, again, is going to be equal to 0.2 times 0.8 plus 1 minus the specificity times 1 minus the prevalence. Okay, so that's going to be equal to 1 minus the specificity. What was the specificity? 0.9. What's 1 minus that? It's going to be 0.1 times, what was the part of this? 1 minus the prevalence. Prevalence was 80%, so what do I put in here? 0.2. Okay, so now I'm going to add these together. I'm going to put this over here. That's that. Just make it a little easier to visualize. And this is going to be equal to this plus this. This is our denominator, right? So what is the positive? Let's see. It's going to be equal to this divided by this. Did I get it right? 0.89. Is that what we got before? No, we got this 0.67. What did I do wrong? I did something wrong. Let's see. Let's see. Sensitivity times the prevalence, which was, what's that? 0.16. Okay, now 1 minus the specificity was 0.1 times 1 minus the prevalence. Oh, I'm sorry, it should have been 0.8. The prevalence was 80%, right? So 1 minus would have been 0.2. So it should have been, what was it again? 1 minus the specificity is equal to 0.1 times 1 minus the prevalence. The prevalence was 0.8, so it should have been 0.2. Did I get that right? No, I got that right. So now why am I not getting this? Trust me, it works when you do it right. Sensitivity times the prevalence. Could I have gotten this wrong? Sensitivity times the prevalence, 0.2 times 0.8. Okay, sensitivity times the prevalence again. Sensitivity times prevalence plus 1 minus the specificity, which is 0.1, times 1 minus prevalence, which is 0.2. And it should be this over the sum of these two is equal to the sum. I'm sorry. Point. Whoops, excuse me. Let me get this out of the way. Sensitivity and prevalence. This is
minus prevalence is 1 minus 0.2.
Right. 1 minus 0. Right. 0.8. Yes. There you go. I did it backwards, didn't I? Okay. You got a good catch. Okay, let's do this again. Okay, so we have one sensitivity times prevalence is 0.16. The second part of this, 1 minus the specificity is equal to the specificity is 0.9, so it's 0.1 times 1 minus the prevalence. The prevalence was 20%. So 1 minus the prevalence was 0.8. Okay, so now it's going to work. Okay, this is equal to the sum of these two, right? These are the two ways for us to get a positive result, false and positive, and it comes up 0.67. Okay, you see what we were doing wrong there? Okay, we kept looking, we kept thinking, it happened because I wound up giving you a specificity and a prevalence that kind of like we're the same numbers, so like that. So when you tried to find the inverse of them, it like confused things a little bit. Okay, but you get that this actually worked when we did it right. Okay, that same positive predictive value. This is a conditional probability. So you can use this tool to calculate this, use Bayes' theorem, this idea of this relationship between these conditional outcomes. You can use this tool to apply it to this kind of test, a diagnostic test, to calculate the positive predictive value without having to, you're given that you know these various parameters, without having to go back into the population and really do a lot of recounting or something like that if you have this information available to you. Okay, so and the main other takeaway point from this is to understand what is a false positive, a true positive. It's really easy to get this mixed up. So a lot of times it may be good for you to use a table where you actually have this marked off for you, so you remember where the false positive and true positives go in this. It's very easy to confuse these. And the other takeaway is that if you have a low prevalence condition, right, then the sensitivity of the test can be particularly important, because when there's a low prevalence in the population, you have a lot greater chance of getting false positives So you're going to be in a situation where you're going to have a lot of false positives, which means that the predictive value of a positive test is much reduced. Okay, so just keep that in mind. And these little details will come up on exams and on homeworks and stuff like that. So now what I would like to do is I would like to go over to the PC, and I'm going to look at the data files that we started to go over before so that we can start to figure out what we want to do with our project information, with our demographics for our project. Okay, so now let me go in here, and I'm going to turn over, I'm going to make the PC the presenter. Okay, and I'm going to make it the presenter. I'm going to open up our data file. Again, from the project file, we have, let's go to the lab here, and under the projects tabs on Blackboard, we have a number of files. The first file that we have is called a code book. Okay, and second file that we have that might be of some interest right now is called a questionnaire. Okay, so particularly for you guys that were online that missed this earlier when we got started at the beginning of this session, I'm going to open these up and I'm going to take a look at them. The New York City Community Health Survey is a telephone survey of some 20,000 individuals. And they're asked a variety of questions. In fact, they're asked something like 200 questions. I don't know how they get people to participate in this, to stay on the phone or to get involved with this. I don't think they pay them. But apparently you get enough people that actually will stick with this and answer their questions. I'm going to open up the questionnaire just so we can see what's happening when these surveyors call these people. And this basically describes, this document describes how they perform this survey. Okay, so in this case, what's happening is that they have a specific script that they have to stick to. Hello, my name is blank, and I am calling on behalf of New York City Department of Health, so on and so forth. We're conducting an important survey. You don't have to give me any personal identifying information, so on and so forth. And if they refuse, they put in a code number. This is what happened when I call this randomly selected number. Now, there's a certain amount of bias to this, right? What's the first bias? You have a phone survey. Person's got to have a phone. So if they don't have a phone, they're not going to be included in the survey at all, right? So you'll see sometimes they may make some corrections to this. They may adjust this data various ways. So when you look on a Blackboard, you'll see they're adjusted value. There's the raw data that you can download, or there's adjusted values that you can download. So they attempt to reconcile, the bias here, because of like the way that this is done. But now once they get this person's agreement, they ask them what their zip code is. They ask them what borough that they're in. Maybe they deduct that from the zip code. What borough they're in. They ask them, are you an adult? Yes or no. Obviously, if they say no, then it ends right there. And then, like you say, it says, if they answer a certain way, skip to a certain question, and so on and so forth. So what do these questions look like? What's your primary language? What's your health status? Okay, given excellent, fair, so on and so forth. What's your health status? And they'll record this information as they go through this survey. And they will ask and hope for answers on all of these different questions. Okay, so now they're inputting this data as they go through this survey. Move this out of the way a little bit. And as they go through this survey, they are recording this data. And this data eventually goes into a database. And that database, they don't write excellent, for instance, remember the first question that was beyond those core questions was, what's your health status? Well, here, general health is the name of the variable. Remember in SPSS, the variable name couldn't have any spaces, right? So here's general health, all one word. Has to start with a letter. There's a maximum length. It's pretty long these days in the latest versions. It used to be quite a bit shorter. And they happened to put in here what the question was. They could have left that out. They could have made us go back to the code book to look that up. but they happen to leave it in this code book. Okay, and well, the answers are going to be 1, 2, 3, and we actually have the numbers of responses they got for each of these. So this is actually not just a code book, but actually does contain some data, some results on what happened. Okay, but now if I go through these, we can see. Let's see. Do you have health insurance? That's something that may be relevant to a lot of us, right? Because we're talking about flu vaccine. We might want to know if you're more likely to get a flu vaccine if you have health insurance. That question might be relevant to us. What kind of insurance do you have? Let's see. You have more than one person you think of as your personal doctor, right? A lot of people don't have a personal care physician, right? Some, in fact, 963. But however, most of the people in this survey that answered this question said that, yeah, they have somebody who consider personal care physician. I'm kind of surprised that number's that big, right? Because I'm sure, especially you younger guys, younger people, right? You probably don't go to a doctor much, I would think, right? Especially males probably don't go to a doctor that much. So most of them, when they answer that question, who knows if they're really answering honestly? Maybe this person that they consider their personal care physician haven't seen for 5 years. They don't really ask them that question, do they? Well, actually they do, right? Physical, if you had a physical within the last 6 months, 5,000 out of the people that more than 50%, well more than 50%, say they had a physical within the last 6 months. Seems like a little odd, right? Right. So maybe there's a little bit of bias here. People have phones. People are responding to the survey. Maybe that's something they have to correct for. That's not our problem for the most part. We're gonna worry about just what these numbers are. We're gonna take this just the way they answered the question. Last time you needed to contact your primary care physician. There's going to be all sorts of stuff in here in terms of asking about exercise, asking them about whether they've ever been diagnosed with diabetes. Gee, people that have diabetes, that have been diagnosed with diabetes, they're more likely to go for a flu shot, or less likely. People that drink a lot of sodas, people that drink a lot of fruit, that eat a lot of fruits and vegetables, right? These are all people who have different mental health statuses. Think of 1 month in the last 12 months when you were most depressed, anxious, so on and so forth. During that month, so on and so forth, and it'll ask for various responses that will give them clues to a person's mental health status, and so on and so forth. And this data is all represented in the SPSS data file. So I'm going to minimize this now, and I'm going to go to the 2 forms of that we have. One form that we have is, where is it now? One form that we have is a CSV file, comma delimited file. Okay, and that comma delimited file will open in a moment. That comma delimited file can be imported and opened into Excel, and it shows general health status, number 5, number 3. So this line across represents one case, one person, one respondent. And there are many, many respondents. I think there's something like 18,000 or 19,000 respondents. They may not have answered every question. This person didn't answer that question. Right? A lot of people, several people didn't answer that question. I wonder what question that is. Okay. We're going to take a look at that and see what question. How long did you have to wait for an appointment the last time you went to your primary care physician? Well, those are the people that maybe they don't have a primary care physician. That's why they didn't answer that question. Okay, but we'll be able to look at that a little bit better. A lot of the times, if it's missing information, we may want to make a judgment on how we're going to deal with that missing information and why they didn't respond. So the only problem with this is in Excel, these numbers really don't mean much to us, right? We can do calculations based on this, means, and we can sort the data, we can make tables out of it, and so on and so forth. But we have to go back to the code table to figure out what this stuff means. Okay, so let's take a look at the same data in the SPSS. Same data in SPSS. When we open it, it's going to look very similar. It's going to look very similar to the input that we had. I'm going to go over here. I'm going to hide that. It's going to look very similar to the data that we had in Excel, right? 1 through 5s, right? And, insured, 1s and 2s, ones, twos, threes, and fours, whatever. That might also, this might be insured and not insured. This might be the type of insurance that they have, and so on and so forth. Well, how do we know what these numbers represent? Well, we can go to our variable view, and we can see for every column that we have here, like the first column is ID, second column is general health status. If I go down here to variable view, it'll tell me, well, for general health status, let's see, what does that mean? Well, it's self-report, whoops. I don't want to stretch all of these. Let's stretch that one. Notice I can spread this out just like I can in Excel. But you want to make sure you don't select all of them. Self-reported general health status. That's what they were responding to. Self-reported general health status. And are the values, they're not coded in here, are they? Right? So we would have to go back to the code book and tell SPSS, well, a 5 means excellent. A 4 means good, very good. A 3 means good. 2 means, and so on and so forth. You would actually have to code this information in. This variable is coded in, very good, average, or poor. This variable is already coded in, right? So I can see that if I go back to my data view. If I go up to view and turn on value labels, it actually will notice it didn't substitute for this variable because it wasn't coded. But this variable has been pre-coded for you. So you can see what those numbers represent. So insured gateway, so on and so forth. Some of these are numeric variables. Some of these are categorical variables. Let me go back to the variable view. Okay, and if you go over to the end here, you'll see if they're categories, nominal variables, or if they're scalar variables. Okay, and let's see if I can't find, oops. Here's a scalar variable here, average mood. That was some sort of scale, presumably. Let me see if I can find that a little bit. Number of 12-ounce sodas consumed per day. Scalar variable. People are telling them the number of sodas. What's your age? That's a number. Could be years, could be months or something like that, whatever they translated it into. If we have weights, you would want to know whether it's kilograms or pounds, and so on and so forth. So some of these are scalar variables. Some of them are nominal variables. Now, you may need to examine this because, for instance, I could tell that there's a few places where it got it wrong. Place of birth. It thought it was a scalar variable. Why did it think it was a scalar variable? Because it may be that there are many conditions that they gave them. For instance, they might have a number for each country or something like that, or a continent or something like that. So it could be there were 80 choices there that the surveyor could use. So that number is 1 through 80, and SPSS interpreted it as a nominal variable, a numerical variable. It's really a nominal variable. So you would have to go back here and change that to nominal variable yourself before you used it. Why is that important? Well, 2 reasons. One, so you correctly identify the variable. The other is because there's certain analyses that you may want to do that SPSS may block you from doing for that type variable type. So you can't do the analysis that you want to do. So if it won't let you do it, one of the things you might want to look for is it correctly identifying the type of variable that it is. Okay, so there's a lot of stuff in here that we could, marital status is a nominal variable and so on and so forth. Okay, so let's take a look at some of the stuff we might be interested in doing here. Okay, so now we're interested in demographics. Okay, and now you're going to have to make some sort of judgment as what might be relevant or what might be of interest to the study that you're doing. So now you're doing a study on there were choices with flu vaccine. What were the others? Diabetes. Okay. So we might be interested in age, might be interested in gender, we might be interested in diet, exercise for diabetes, so on and so forth. We might want to get a look at a lot of that kind of information, right? So if I go up here I'm going to go back to the data view. You don't have to do this. I'm going to go up here to analyze, right? And I'm going to say to myself, well, gee, one of the first things I might be interested in is gender, okay? So let's go into here. Let's go into descriptive statistics. Gender is going to be a nominal variable. So I'm interested in frequencies. How many people are male? How many people are female? Okay, so now I'm going to quickly scroll through here. Maybe not so quickly scroll through here. Maybe I'll get lucky to see if they got it under gender.
It's under sex.
It's under sex? Okay.
I don't think it's alphabetical.
There you go. Yeah, well, this is, as it happens, the way it's displaying the frequency.
I think it's specified like sexuality.
Oh, yeah? Okay. Okay, so I'm going to move that in there. It might be coded, it might not be coded. Okay, so now, if I go into statistics, right, am I interested in the mean here? No, I'm not. In fact, I'm kind of disappointed that it didn't lock this out. And, so I couldn't do this kind of stuff. Because male or female, what does mean mean? Right? That's person has one testicle and one breast, right? That's the reason. I mean, what other conclusion can you draw from doing that analysis? Right? So we are interested in charts. So for instance, we might be interested in a bar chart or a pie chart. And there's a few ways we can make charts here. Remember, we can actually go with the graphs function as well. But I'm gonna do that, and I'm gonna say, okay, charts. I'm interested in a bar chart, and I want chart values, frequencies, or percentages. I'll stick with frequencies for now, and I'll say, okay, let's see kind of result we get. Output window pops open. That's what happens. You guys at home, you missed us playing around with this before we got started in the regular class with the people. That's the advantage of coming in here. If we're here early, we can tinker a little bit, answer a few questions. So what does this give us? This gives us a table, right? Frequency table. There are 3,500 males in this survey and 5,239 females in this survey. Could be because there's more females in the population than males. Could be that the females were more willing to sit on the phone and answer all these questions. Who knows? Right? So who knows if that really represents general population. If it doesn't represent the general population, that might be one of the adjustments that you're going to make for these various results. And here it is. Here's the information displayed graphically. Okay, look how much easier it is to interpret what's going on here graphically rather than in the table. Let's get a look at another possible outcome. Analyze descriptive statistics. This time, I'm going to look for a numerical variable. Now, obviously, if you want, you can do a country of origin. It'll give you all the different countries and so on and so forth. But you might want to look at the various demographics that might be important to you. So there's many nominal variables that might be of interest to you in doing these various studies. I'm just scooting over here so I can see what time it is. Oh, we're late. Okay, so I'm going to go over here, compare me. I'm going to go over here, descriptive statistics, descriptives. I just want to point out to you that if you go in here for descriptives, right, and I pick out a numerical variable. Anybody got a good one here? Age. Okay. Is there a age of diagnosis of diabetes? Is that what that is? Let me get another one. This country of birth. It thinks that's a nominal variable. Demographics, nominal variable. Obviously, there's a lot more categorical variables here. It's going to affect us later on in terms of like what kind of value, what kind of tests that we use, whether it's nominal. So how about sodas? Is that we have something there? How about smoking? This is some sort of numerical variable. I'm going to move it in here just for argument's sake. If I go into options, it gives you a limited number of options for you can analyze, right? You can ask it for a mean, you can ask it for a standard deviation, variance, and so on and so forth. If instead of using that, I had said, let's go to Analyze, Descriptive Statistics, Explore, right? Now, when I move one of these numerical variables, I'm just going to pick that one out here. I can go into Statistics. It's going to automatically do a much more extensive range of descriptive statistics for me. Number one, I'm going to have more options in terms of the kind of graphs that I want to get. Stem and leaf, histograms, and so on and so forth. Numerical variables, we don't want bar charts, we want histograms. And it'll let me do something else, which is it'll let me move another variable in here so that I can compare two groups. diabetics versus non-diabetics for various numerical variables. So I can get side-by-side analyses. I don't want to use this one. BMI. Okay, let's look at average BMI, and let's look at it in terms of diagnosis for diabetes. I'm going to guess that that might be diagnosis for diabetes. And what it's going to do is it's going to take the values for diabetes, a person who has diabetes, for a person who doesn't have diabetes, assuming that that's what that is, and it's going to calculate the average BMI and all these other statistics for the two groups separately, rather than the whole population as one group. I'm going to go into statistics, that's already set up. I'm going to go into plots, ask it to do a histogram for me also. So let's see all the stuff it'll give me. Okay, wow, look at this now. So this is body mass index. Have you ever been told you have diabetes? Yes. Mean body mass index for people that have been told they have diabetes is 30.15. The mean body mass index for people who have not been told they have diabetes is 28.8. Quite a difference. But it also gives you all these other statistics for each of these two groups. And it gives it to you side by side. It also gives you a histogram and a box plot for these. I thought I checked off histogram. Did I not check off histogram? Is that it? Oh, I didn't say okay. There you go. Okay, descriptive statistics. Explore. Now it remembers exactly how I had this set up. Okay, I'm going to click off histogram. Continue. And I'm going to do it again. It's going to repeat it. Except this time I'll get a histogram. For the two, there we are. There's a histogram for the two groups. There's a histogram for people who have diabetes, body mass index. This is a histogram for people who don't have diabetes. Okay, is this what kind of distribution is this? Is it normal? It looks like it's skewed to the right. There are some people with very high body mass indexes that are tending to pull the average higher than the median, right? Pull it away from the middle, right? So it's skewed to the left. But we'll be getting into that in a lot more detail. Okay, so guys, I think this is an introduction. You should be able to play around with SPSS, produce some interesting tables and graphs, and get a start on where you want to go with your project. Okay, now the other thing you might want to do is do a little bit of background research. You're doing it on diabetes. What's the relationship between there are articles published, relationship between BMI and diabetes, relationship between sugary drinks and diabetes. People have done other studies, right? So we have an expression, it's better to stand on the shoulders of giants, right? You don't have to invent everything yourself. So, and you'll be able to use these in references, as references later on when you put together your presentation and your poster. Okay, any questions, guys? No? Okay, so pretty clear, right? This idea of probability and these